Welcome to our customers, partners, contractors, wholesalers, and engineers from coast to coast to coast of our beautiful country. Good morning and good afternoon, as the case may be. While I thank you for your time to join this webinar today, I'm sure you will enjoy the insights on refrigeration industry, our semi-welded and bonded product range, their applications, features, and innovative designs, which are efficient and environmental friendly. The brief agenda is to talk about refrigeration trends, semi-welded products, DX versus flooded evaporators, U-turn separators, Alfa Nova product line, and Brazed line. My name is Sandeep Kumar, and I'm heading the equipment heat exchanger segment within our energy division. The main speakers today are Gracia Ayala, business developer and specialist on industrial refrigeration, and Christian Kemp, product and application specialist from Central Organization in Sweden. We have pre-recorded part of this webinar, and in the end there will be live question and answer session. So please post your questions in the chat box and we will try to answer them in the end. If there are still some unanswered questions, we will revert back to you. Now, please enjoy the webinar. Over to you, Christian.
So refrigeration is basically about your fridge. It's about keeping things cold and occasionally hot by using a refrigeration cycle. And the most common application is, of course, the refrigerator or fridge at home. But as we all know, things can be a little bit bigger when we go into the commercial or industrial part of refrigeration. An industrial refrigeration plant is basically made out of the same components as the refrigerator at home. We have a condenser and a compressor and an evaporator, and then some sort of fluid or refrigerant, which puts everything together. And as one knows a little bit more about this industry, this refrigerant has a tendency of being a bit problematic. Traditionally, a refrigerant is, in addition to its ability to work as a thermal fluid, measured on its ozone depletion potential as well as its global warming potential. This graphs with the relative ozone depletion potential horizontally and the relative greenhouse warming potential vertically shows you this. And basically, you don't want to be up here in the right top corner. The really old so-called CFCs and HCFCs freon had a very high ozone depletion potential. Therefore, it was decided through the United Nations Support Montreal Protocol to phase out these refrigerants and replace them with something less harmful, the HFCs, which is the refrigerant that we are seeing in today's HVAC chiller and refrigeration application. The problem with these refrigerants is that they are having a very high global warming potential. Simply, they are much worse to use one of these refrigerants compared to releasing CO2. Therefore, it has been decided to phase out these refrigerants as well as replacing them with something else. The natural choice would possibly to change to a natural refrigerant. That is things that you can find out in the nature, like CO2 and ammonia, as these are very high efficient refrigerants with no global warming potential or ozone depletion. However, these have some drawbacks which has resulted in the new refrigerants, so-called HFOs. If we sum up the situation, we can conclude that the old freons such as R134A, R22, R404, they are relatively easy to use. They are relatively cheap to buy, but unfortunately they are not good at all for the environment. Therefore, they are effectively being banned or taxed out in most markets today. The development is, of course, the new freons, the HFOs. These are relatively efficient, have a considerably lower environmental impact compared to the old freons, but on the downside, they are quite flammable in some cases, and in the long run, considering that we in this industry has changed the refrigerant once every 10 years or so, one might question if they are really here to stay. That leaves us with the fluids the industry once came from, the natural refrigerants such as ammonia, CO2, propane. These refrigerants are very efficient. They have no real environmental impact. However, they might be toxic like the ammonia, only work under very high pressure like CO2, or be flammable like propane. These new trends in the refrigeration market leads to some challenges when it comes to the use of heat exchangers for condensers, evaporators, etc. We in Alfa Laval has taken up these challenges, and we are now to present to you our solution for efficient and safe plate heat exchanger from the natural refrigerants. So the first question here is, where will I find a heat exchanger in a refrigeration system? Well, the answer is approximately all over the place. Traditionally, we will have plate heat exchangers, evaporators, and condensers, but we can also find them as DC superheaters, subcoolers, economizers, and not at least at compressor oil coolers. Depending on the system size and the refrigerant use, these heat exchanger can be of brazed or fusion bonded design, or even semi-welded types. But before we are going to look more deeply into each of these technologies, let's spend a minute on seeing where to use which type of heat exchanger. If we had identified a need for a plate heat exchanger, for instance, as an evaporator, condenser, or oil cooler, one has to ask themselves what requirements are to put on this application. If the application is, for instance, dirty water or dirty brine, which require frequent cleaning of the heat exchanger, it should preferably be an openable one, and then the semi-welded plate heat exchanger is the best choice. The same goes for if the application uses a secondary fluid like calcium chloride or salt water, which corrodes stainless steel. Then the semi-welded plate heat exchanger with titanium plates is the best solution. Or if we are dealing with a high capacity duty where the industrial size of the semi-welded plate heat exchanger makes it the preferred solution. If nothing of the above is applicable, one can ask if the heat exchanger needs to be from copper. If that's the instance, for instance, we are operating with ammonia, or we would need to operate with, for instance, tap water application, then we will recommend the Alfa Nova, the 100% stainless steel fusion bonded plate heat exchanger. Coming that far, for everything else, we would recommend a brazed plate heat exchanger due to the thermal performance and the fact that this heat exchanger is using the majority of material for heat transfer and therefore being the most affordable solution. And with that said, let's have a closer look on the semi-welded plate heat exchanger. A semi-welded plate heat exchanger is made up of the same concept as a plate and frame heat exchanger. There are a frame and a pressure plate, which together with the tightening bolts makes up for the pressure vessel and form the main unit. There will be a carrying bar and a guiding bar, which helps to keep the plate back straight. And there will be feet and a support column, which makes sure that the structure stays where it's supposed to be and not go anywhere else. On the frame plate, you will find the ports as well as stud bolts and linings, which make sure that the incoming fluid doesn't get in contact with the carbon steel frame plate. The seam welded is built up like the traditional plate and frame heat exchanger with plates, which could be of either 316, 304 or titanium material. The plates are pressed so that when they are stacked together, they form a channel with a very efficient thermal conductivity pattern, always giving turbulent flow. By changing the pattern of the plates, in most cases by changing the herringbone angle, channels with different thermal and hydraulic characteristics can be formed, optimizing the design against any type of application. In short, the lower the angle of the herringbone is, the lower the pressure drop, but also the lower the heat transfer. On the other side, plates with a higher angle of the herringbone would generate more pressure drop, but also more heat transfer. Then there is a third alternative to combine two plates, one high and one low, and then we get some sort of intermediate performance. The difference between a seam-welded plate heat exchanger and a standard gasket plate heat exchanger where all plates are being sealed off with the gasket, is that in a seam welded plate heat exchanger, every second plate are welded together to form a cassette, which gives a very strong heat exchanger channel with a smaller gasket exposure. The cassettes are then stacked together and sealed from the outside with the field gaskets, which would help to form the so-called gasketed or field side, and the ring gaskets, which will form the intersection between the welded side, and then putting onto a frame, looking like something we have up here in the top right corner. This in all gives a heat exchanger with a very good firm performance. However, the design of the seam welded also brings some additional benefits for the cascade heat exchanger, which we will describe more in detail. One benefit, very convenient in the refrigeration business, where we are operating with low temperatures and want things to stay cool, is that the seam welded is opposition to rigid heat exchanger like a shell and plate or shell and tube can take freezing without breaking the structure of it. In the case of a seam welded plate heat exchanger, the difference in volumes will be taken up by the gaskets instead of being transferred to the structural part of the construction. This also makes a seam welded plate heat exchanger the optimum choice for application with a high risk of thermal and pressure fatigue. Just like the case with the freezing, fatigue forces will be taken up by the gaskets rather than transformed into the material like plates and cause cracks, which we find here in this picture in the middle of this slide. Alfa Laval is offering a range of seam welded plate heat exchangers starting from the 3-inch M6MW and going up to the quite big MA30W with the 12-inch connection. This makes it possible to find the right unit for the right application. Pressure-wise, the standard seam welded plate heat exchanger comes with a 300 psi design pressure for evaporators and condensers, but there are also units available for 600 and 900 psi for CO2 and cascade and heat pump operations. And with that, I will leave to Grecia to talk something about the features in the seam welded plate heat exchangers.
Thank you, Christian. Good afternoon, everyone. Alfa Laval has a new generation of plate and frame heat exchangers that can help you reduce your energy bills, prolong the operation, and simplify maintenance. Some of the new features are curved flow, offset gaskets, omega port, 5-point alignment, power arc, clip grip, and T-bar roller. Together, they offer improved thermal efficiency to cut energy costs and help you meet your sustainability goals. They also offer greater mechanical reliability for longer equipment life and reduce the risk of downtime in your operation. Easier serviceability to keep maintenance to a minimum and to save you time, labor, and money on that service. These features are what define the next generation of gasketed plate and frame heat exchangers, and they are unique to Alfa Laval. Let's talk briefly about 3 of them. Type, for instance, is a sealing system that enables long-term performance for high pressure and high temperature. The weld is now located outside the gasket ring groove, allowing stronger ports that can extend the gasket lifetime, even in applications for high pressure requirements. Second one is curved flow distribution, and this was designed for a better utilization of the whole plate and frame surface. This feature eliminates dead spots, providing higher thermal efficiency with the reduced risk of falling. This means energy savings, lower maintenance costs, and less time worrying about unplanned stops. The third one is clip grip. Clip grip offers superior fastening to the plate and are easier to mount. The unique design prevents sneaking of plates at closing, and the result is long-lasting gaskets and less maintenance is required. Now let's talk about a quick comparison between a flooded evaporator and a direct expansion unit for a typical recreational application. With a flooded chiller, we can have a closer approach between suction temperature and glycol outlet temperature, allowing savings on energy consumption on the compressor by having a high evaporation temperature. On the opposite side, direct expansion requires superheat value in order to guarantee no liquid carryover to the compressor. This superheat leads to a tighter temperature approach. LMTD, which is the temperature relationship between inlets and outlets, temperatures dictate the size of the heat exchanger. In this case, with the flooded heat exchanger, we'll need less heat transfer area than direct expansion. This translates into a lower cost of the heat exchanger. However, you have to put a separator on top. An optimized separator can allow us to work efficiently at the highest possible suction and reduce the ammonia charge that can end up being very close to a direct expansion application. Talking about separators, most of you have heard about our U-turn separator. Alfa Laval U-turn is a liquid separator that comes pre-mounted to the heat exchanger. Rather than the conventional one, which separates only by gravity, the U-turn uses 4 methods of separation: agglomeration, surface tension, gravity force, and centrifugal force. The efficiency of this evaporator has been a great surprise for our customers. Some of the advantages are small footprint compared to a traditional surge room. Also, dramatical reduction on ammonia charge, achieving 0.5 pounds per ton of refrigeration. The U-turn also allows us to have high efficiency. We estimate that the suction temperature can rise due to the optimum control of the liquid level, generating annual savings between 3 and 6%. Unit is only available for ammonia, which makes this a green solution for your application. Now let's talk briefly about brazed heat exchangers, the range and denominations. We have 3 ranges of heat exchangers. First one is the AC Alpha Chill series that is specifically developed for direct expansion evaporators and condensers. Second one is the CB General Brazed heat exchanger. And the third one is CBXP and AXP that are meant for extreme design pressure ratings for CO2 duties. Alfa Laval CB is one of the largest product lines that we have and is used for several applications, mainly liquid-to-liquid applications, for instance, for HVAC, industrial heating and cooling, as well as refrigeration as a desuperheater, condenser, or evaporator. There are products in different sizes, channel volumes, and pressure ratings. It's important to mention that all of the units have CRN available. Alfa Laval AC product line is developed for the refrigeration market and the 2-phase applications, such as evaporators, condensers, subcoolers, as well as economizers. These heat exchangers support a wide variety of HFCs, HFOs, including propane, refrigerant 1, 2, 3, 4, XY, and CO2, of course. CRN is available for all models. AC line has a unique integrated refrigerant distribution pressed together with the plate to ensure the highest level of quality and performance reliability in an evaporation mode, allowing a good subcooling used in reverse mode as a condenser, for instance. Then we have the AXP line. As I mentioned before, this is primarily designed for cascade applications as well as CO2 requirements, meant for heat pumps, heat recovery, and the maximum pressure, design pressure that these units can work is now at 2,233 psi. Alfa Laval Alfa Nova is a 100% stainless steel heat exchanger dedicated for applications with ammonia, hygienic, HVAC, and cascade. These units are highly used as well for oil coolers and relatively small condensers or evaporators. This is the end of the presentation. We'll allow some time for your questions. Please write them down in the chat box and we'll discuss them. But before, thank you for attending. Next seminar will be high pressure plate and frame heat exchangers for heat pumps and cascade systems.
Okay, thank you, everybody. This is Jamie Hod here. I'm one of the producers, and I'll extend, first of all, a big thank you to everybody who has attended, and to Sandeep, Christian, and Gracia for the time and energy that they've spent in preparing the material here. We're going to be open to questions at this point. I'm going to be going to the Q&A chat here. First one that I will be giving to Sandeep. Question has come: are the plates in a heat exchanger stamped, machined, or 3D printed?
Thank you for the question, and it is quite important and thoughtful question. For plate and frame heat exchangers, as well as for brazed plate heat exchangers, both, the plates are pressed.
Okay, thanks again, Sandeep. Maybe you can take the next question here. This is with regards to fouling. When we have high fouling media, can you still use a semi-welded heat exchanger with welded cassettes? I think that, that's a common question seen too.
Again, a very, very important question, because we carry a lot of misconceptions around plate and frame heat exchangers in the market that they will have a tendency to foul more. Let me give you a surprise to everybody that Heat Transfer Research Institute had conducted kind of study and compared plate and frame heat exchangers with that of shell and tube heat exchangers, very specially for fouling. And what was found that because the plates have corrugation and a pattern inside, they have a tendency to create much higher turbulence, which leads to very high shear stress value, and that leads to much less fouling. In the case where they had considered the shear stress value in the plate and frame heat exchanger was, let's say, 60 unit, which is in pascals, and in shell and tube they found it was 1/4 of that, which was 15. And the result of that study concluded that fouling in plate and frame heat exchanger was 50 to 70% lower than plate and frame heat exchanger. Now, the question was very specific to semi-welded plates, and semi-welded plate heat exchangers are based on plate technology, so they will also have much less fouling as compared to shell and tube heat exchangers. Very important question. Thanks once again.
All right, thanks very much. I'm gonna give the floor to, or give the microphone to Gracia for the next two systems too, or next two questions, pardon me. There's a question specifically regarding seems that the audience member was impressed by having an ammonia charge of a 1/2 pound per ton. And they've asked, can we install this? Has this been installed, or any systems operating in Canada at this ammonia charge level, a 1/2 pound per ton? And is there any experiences that can be shared with us too?
Thank you, Jamie, for the question. Yes, it's actually very, very impressive. The first installation was done in UK, and the interesting part of it is that it was for a hospital. After that, Alfa Laval gained a lot of confidence and started to install these units across the globe. We have hundreds of installations now in Canada, and we have achieved very, very low or even ultra low critical charge ammonia into our systems. Just to give you some examples, we have a lot of presence in BC with Canlan. We also have applications for not only recreational, but food applications such as Fiera Foods. And the newest one that we got is with Natural and Agropur, that we are achieving 0.37 pounds of ammonia per ton of refrigeration. So this will be into the critical charge more than low charge even.
Okay, well, 0.37, that's setting a new benchmark here too. Second one, this is a mechanical question. What is the maximum design pressure that, actually this is a two parts question here, because they seem closely related. What is the maximum design pressure that semi-welded heat exchangers can reach? And any advice to be giving on preventing heat exchanger ruptures at high pressures?
Thank you, Jamie. I'll take that one too. And the maximum design pressure that the semi-welded line can go up to is 900 psi. 900 psi will be the standard requirement for the refrigeration systems, but we also have another three ranges more. So we have 900, 650, 450, and the regular evaporator and condenser at 300. In regards of the advice on preventing heat exchanger ruptures at high pressure, the greatest advantage of having a semi-welded technology is that any fluctuation in either temperature or pressure can be absorbed by the gasket. So the gasket allows us to have that flexibility on the heat exchanger compared to other welded technologies that when a pressure shock comes, it will burst. Semi-welded technology can absorb those shocks in a very, very good way, and that will give a longer lifetime than other units.
Okay. I have a new question that's come in for Gracia. It's specifically with oil actually within the heat exchanger. And how can we be sure that oil is not going to be trapped inside the heat exchanger? I'm assuming that's oil from the compressor mainly too that will carry through the refrigerant system.
Yes, well, we have two options for that. The first one will be that before it gets into the heat exchanger, it should be separated. So normally, a common practice is to put the oil separator in the bottom of the at the lower level than the evaporator, and by gravity it will separate and then it can be drained. The second one is that we can also provide a port in the back of the heat exchanger where the oil could be potentially drained. This practice is not very common in Canada, but we have seen many options in other countries.
All right, super. I'm going to turn the microphone back over to Sandeep here, and there's a question regarding the Alfa Nova line. Can the Alfa Nova line be used for ice rinks?
Yeah, thanks for the question. Yes, the short answer is yes. Alfa Nova is our 100% stainless steel fusion bonded heat exchanger. And because it has 100% stainless steel, it does not have any copper. It can also be used as ammonia condenser and also as evaporator for some smaller capacities. So yes, the answer is yes. If you have, let's say, glycol as a fluid, Alfa Nova can be utilized as a condenser or evaporator for ice rinks. But in case you have calcium chloride as a brine, then we will have to switch to semi-welded plate with titanium plates. because of the corrosion which will come from the calcium chloride brine. So I hope that answers the question.
Yeah, hopefully it does too. That's certainly very thorough. I'll switch to Gracia. It looks like we have one more question at this point. And this is with regards specifically for heat pumps, cascade systems. Can a U-turn centrifuge, okay, U-turn separator, can this be used in both systems in the cascade? Or another way of putting this, can the U-turn work on both sides on a cascade application like CO2 and ammonia?
Yes, definitely. We have multiple applications where we can use in a cascade system a U-turn. This will give us the opportunity to have the most compact heat exchanger and separator and achieve the highest suction while saving saving energy from the compressor consumption by raising the suction temperature. So yes, definitely we have already 2 installations, one in Quebec and one in BC, with this arrangement.
All right, thank you, Gracia. There is actually one other question that's come in here too, and maybe Gracia, we'll let you answer this one because it pertains to your part of the presentation. Asking if direct expansion heat exchanger units, if they're co-current or counter-current flow. The attendee thought they heard counter-current flow, but they noted co-current on one of the slides.
Yes, thank you for the question. It's a really good question. Normally for flooded, we do co-current. For direct expansion is counter-current flow. The reason behind that is that in DX, we want to take advantage of the big temperature difference between the suction temperature and the inlet temperature. With that, we can reduce a little bit the heat transfer area, but it still will be way more than if we start evaporating with the flooded. I hope that answers the question.
Okay, I think that'll do. I think that, or I'm assuming that does here. And just waiting another second. I think in the meantime, I think we're wrapping up here. I'll put it over to Sandeep certainly for a final sign off or anything else for what's next coming up over our summer season too.
Yeah, so thanks, Jamie, and thanks, Gracia, Christian, and everybody who are involved in making this event. We have Stephen and Denise in the background helping us, and of course, Jamie Hodd, who is our general manager for energy division, but he also is acting as producer for this event. Thanks, everybody, and thanks, everybody, for joining this event. Thanks for taking out this time and asking very important questions which are useful to the entire audience. I'm happy to announce that we are going to come out with a new webinar, which will be really very, very interesting. Topic of today, which is going to be high pressure heat exchangers for cascade and heat pumps. And you will hear shortly from us about this new webinar and the date and time, etc. Thanks, everyone.